I am Anil Kumar. Welcome to my YouTube channel and the website globalmathinstitute.com. Let me thank all the viewers and subscribers for watching my videos and contributing in the form of sharing questions and providing suggestions. This is an excellent video where we are having a lesson on statistics and probability. I'm going to discuss at length how do we find the conditional probability when two or more events are given. We'll look into three different ways. One, using the Venn diagrams, and then using rows and columns, that is to make two-way tables, and then we'll look into making tree diagrams. Now, these are three very interesting cases which can help you actually provide simple solutions to difficult questions. So, let's enjoy the class with Emmy. Learn as she learns. Remember, you can always join my classes by sending me an email on the address given. You can register for online one-on-one classes with me and excel. Hi, Amy. How are you doing?
Hi, sir. Yeah, I'm doing well, thank you. How are you?
Very good. Very good. So today, what do you want to do?
I was hoping if we could just kind of like roundabout come to a finish of this chapter with probability and conditional probability and stuff.
Sure.
Yeah. So I think the last chapter we finished on last week was the conditional probability stuff.
Yeah.
So just a quick recap of that would be good, and then move on.
Okay. Yeah, we started with these Venn diagrams and then went to conditional probability. Correct.
Right. Let me just quickly zoom in. So I don't know if we covered example 6, but oh yeah, so this is the formula that I was talking about, and you know how you said that you obviously draw it out, which is definitely more helpful, but the formula is also there if you like. It is easier sometimes when you get into a bit of a flow and you want to double check. Yeah.
Okay, example 6, let me tell you one more thing about it. Can you please read the question?
Yeah. So A and B are two events with probability A as 0.6, probability of B as 0.7, and probability of A or B as 0.9. So find the probability of A and B.
Right. So we actually call this as principle of inclusion and exclusion. So that's a name which is very important to understand. It is called principle of inclusion and exclusion.
Yeah.
Yeah. So what I find, globally in different parts of the world, we see things differently. The same question, we see it very differently. So that's the fun part. I really enjoy that part. So now let's look into this question. I'll try to do it my way, and then we'll see how it has been solved in your book, right?
Okay.
So when you are given A and B are two events where probability of A is 0.6, probability of B is 0.7. So if I add 0.6 and 0.7, what do you get? You get some number which is more than 1, right?
Right, yeah.
Okay. And probability of A union B is 0.9. Find the probability of A intersection B, right? So clearly, when we are talking about an event which includes two events A and B, let me just sketch the Venn diagram. This is one event, that's the other event. And we are saying that probability of A, let's say this is A for us, is 0.6. And this is B for us. We're saying probability of B is 0.7. And we are also given that union is only 0.9. So if you add them up, so probability of A union B is what? Is given to you as 0.9. You get the idea. But if you add 0.6 and 0.7, you get what? You get 1.3, right?
Yeah.
You get 1.3. So why is it so? It is so because when you had probability of A, you're counting everything which is being shown here. You see that? And when you count probability of B, you are counting everything which is being shown with these blue lines. Now, union will mean that, the center portion, it has been counted twice. You get the idea?
Yeah.
Since it has been counted twice, that is why we are getting the sum as more than one, correct?
Oh,
We have
right.
to take it out. So that is called, it has been included twice, and therefore we need to exclude it. So that is the principle of inclusion and exclusion. Does it make sense to you?
Right. Yes. So because the center part where the A and B has been shaded in twice, like from your diagram, we have to subtract that out
Yeah.
later or something.
Right. So strictly speaking, probability of A union B is actually probability of A plus probability of B. Take away probability of A intersection B. You get the idea?
Yeah.
So now, each probability, probability A union B is 0.9. And once you substitute these values, you can find that excess value which you got was mainly because of the intersection. You get the idea?
Right.
So now you can do your calculation to get the result, which is probability of A is given to us as 0.6 plus probability of B is given to us 0.7. We need to find the intersection of A and B, and we know both of them, all this is 0.9. So we can now rearrange and find what probability of A intersection B is, correct?
Yeah.
So that is what is shown here also. So if you look into your formula, exactly same thing they're talking about. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. You get the idea? Because this has been counted twice. So we have to remove it. And
so is that a separate formula in itself?
Yeah, it's a formula,
Okay.
but it is like, if you look at it, it is sensibly derived, right?
Oh, right. Yeah.
Logically derived. So that's very important. So that is how you get the solution of this particular example, which is 0.4. Can you please read this part?
You can also use the Venn diagram in the explanation above to find a formula for the probability of B given A. So to find the probability of B given A, restrict the sample space to the set of outcomes in which A has already occurred.
Correct.
This is a subset of outcomes in the restricted sample space in which B occurs.
Correct.
So probability of B given A is I over A minus I plus I equals I over A.
I is the
Where did I come from?
I is the intersection.
Oh, right, okay. Why didn't they just write?
Yeah. So I is the intersection, and the probability of A is A, right? So
Yeah.
I over A, correct? You get the idea.
Okay.
Because conditional probability is when A has occurred. So if A has occurred, then that becomes our domain, or you can say the sample space or the outcomes from which we have to take away what is favorable to us.
Oh, right, yeah.
So when A has occurred, of course, we are into this particular portion, which is which they have split A as A minus I, and I means intersection between A and B, correct? And so probability of B will now be only that intersection part over the sample space, which is restricted to the sample space of A. And so you get this formula, correct? This is correct. So we actually applied this formula earlier also to find probability of many conditional examples, correct? Conditional probability examples.
Yeah.
Right. So can you please read further?
So since the probability of B and A is I.
Yeah, into I, yeah.
Oh, and probability of A is A, then you can write the following multiplication formula for the conditional probability.
Yes.
Which is probability of B given A is the probability of A and B over probability of A.
Yeah, intersection of B with A over probability of A, correct.
Then they cross multiplied, and you can also rewrite in terms of the probability of B and A as the subject.
Correct, you could write that. So probability of B and A is probability of B when A occurred times the probability of A. Very important formula, which has been now derived. Is that clear to you?
Yeah.
Make a note of all these formulas in a separate paper so that you can actually refer to them when required, right? Every
Yeah.
time deriving will take a lot of time, and in
Right.
examination, we really don't have luxury of time, correct?
Yeah, we definitely don't. I'm always running just up until I need to get better with my timing, and I guess that comes with practicing in time conditions at home. But it's hard though at home because obviously distractions and things, people can come in. But yeah, so you definitely kind of need to know that.
Now here, we have one more important thing to check. So Amy, we have one more important thing which we can derive from here. We are saying probability of B when A has occurred is probability of intersection of A and B over probability of A.
Yeah.
Now let us say that we're talking about, let me clear the screen and then I'll describe. Let's say we are not talking about independent events. Okay, let me write here. So if the events are independent, what does it mean?
The probability of A and B equals the probability of A times the probability of B.
Okay. So if we have independent event, in that case, the numerator here, which is probability of B intersection A, and this is also equals to probability of B intersection A because they are independent events, correct?
Yeah.
So in that case, you say probability of B when A has occurred is equal to what? The numerator I could write as product of probability of B with probability of A, correct?
Yeah.
And divide by probability of A. What do I get?
Oh, it cancels.
It
So you just get
cancels.
probability of B.
So it is independent of whether A occurred or not occurred or what happened. You get the idea?
Oh, yeah.
So if you have to show from here that this conditional probability thing is this process was dependent or independent. So that is very straight away seen here that probability of B when A has occurred is same as probability of B.
Oh. Mm.
So if that result is derived, that means the two events were independent.
Right.
Okay.
So if you want to find the probability of B given A, do I just need to find the probability of B?
Oh, if they are independent, right?
Oh,
But if they're not, then this is a general solution. We are basically
right.
looking into the intersection and the domain being A. You get the idea. So look at it very clear. So probability of B when A occurred is intersection of probability of A and B, the common portion which is being shown here, correct?
Yeah. Yeah.
Over the restricted domain of what has occurred, which is probability of A, correct?
Oh, right. Yeah.
That becomes a much easier way of remembering or connecting the two things. Is that okay?
Yeah. Yeah. Clear.
Perfect. So now let's move forward.
So I think example 7 is just like reiterating what you said. We can try.
Yeah, sure. Why not you solve it? Yeah, read and solve.
Okay. So C and D are two events such that probability of C is 0.2, probability of D is 0.6, and probability of C given D is 0.3. So find the probability of C and D. So using the formula that we just found, if you cross multiply, you can find. So probability of
given D is basically probability of intersection of C and D, correct?
Yeah, over probability of D.
Probability of what occurred, right? So you're given all these probabilities, and so you can rearrange and find the intersection, correct?
So so you can do 0.3 times 0.6.
Correct, just multiply it. They're done and they've got the answer right there itself.
Yeah.
So once you get that, you know the probability of C intersection D, which is the numerator for us, and now you can actually find the probability of D intersection C, right? Because this intersection is same, right? Whether you say probability of D intersection C or you say probability of C intersection D. It's the same
Yeah.
intersection, correct? So basically, in this case, this intersection is 0.18 as they just calculated, correct?
Yeah.
So probability of D when C has occurred will be the intersection of the two, but now the domain becomes the probability of C, correct?
Right.
And therefore, we get the result as 0.18 divided by 0.2, that gives you 0.9. And union, of course, use the principle of inclusion and exclusion, correct? So,
Yeah, where you subtract the intersection.
yeah, but you have split them up. You can add them separately, right? Yeah, add them an intersection, take away, exclude it, and you get your formula, correct?
Yeah.
So basically, in this, we learned two things. One is the dependent event formula, how it can be rearranged to also find the probability of intersection. And the union is of the two events is basically sum of those two probabilities take away the intersection of the two, correct?
Right. Yeah. So 2 formulas.
Yes.
I need to make a list of these formulas.
Yes, yes. And also, you could derive, in case required, a condition that whether the two events are dependent or independent. So if probability of B intersection A is same as probability of B, that means it was independent event, correct?
Right. Yeah.
Perfect. Let's move forward.
So I think the top ones are kind of the simple ones we've done.
Yeah.
So we can move on to these red ones with the red little thing.
Yeah, that'd be better. Yeah. Let's look into question number 9. Sure.
Okay. So given that probability of A is 0.42, probability of B is 0.37, and probability of A and B is 0.12, find the probability of AUB. So yeah, that's using the formula.
That's easy. So intersection of A and B is 0.12. We'll write down always in the center, inside out, right?
Yeah.
Probability of B is 0.37. Let's say this is A, this is B. Then we already have 0.12. So 0.37 minus 0.12 will give us what? 525, right? 0.25.
Yeah.
And A 0.42. So 0.42 minus 12 will give us
0.3.
0.3. So once you have all this, union is clear sum of these three, you could add them up, or you could add and take away, right? You could do either way. Now, probability of A.
So do you want it? Should I add up quickly to see the outside?
Yeah, sure.
Okay. 0.42 add 0.25, 0.67, so 0.33 outside.
So this is 0.67, right?
Oh, no. Oh, yeah, that's 0.67. Yeah.
Okay. So now
and outside the bracket, it's 0.33.
So we have outside 0.33. Okay. So 67, and we got outside 0.33. Good job. Because the next question was, what do you mean? Probability of A when you know that B has not occurred, right? Not B, right? Not B. So probability of A, not B, will mean what for you?
So if we do not B first, that's everything outside plus the bit in A.
Yeah. So not B is 1 minus B, right? So 1 minus 0.37. Is it okay?
Oh yeah. What? I keep doing
You could do
yeah, I keep using the Venn diagram instead of like the formulas.
You could do yes.
So this can be written as probability of A and not B over probability of not B.
Yeah, so probability of A intersection not B, correct?
Yeah.
So if you look at it, probability of A intersection not B is 0.30, correct?
Yeah.
So there the Venn diagram is much better. You can easily see the result, correct?
Yeah.
So we can write this as 0.30 over 1 minus 0.37. Is that clear to you? So it's the combination approach which is actually the best rather than remembering so many formulae.
Correct? Oh yeah. That is very good. So let's quickly just do some calculations. Sure. 0.476.
Okay. So let's move forward. I'll just clear the screen and we'll move forward.
Cool, cool.
That was interesting. Not B case was very interesting, actually.
Yeah, yeah. I think that's where they try and trick you, you know. But
Yeah.
sometimes they can bring in more like circles, so then you'll have like a lot more going on, which can be tricky.
That's so true. Yeah.
I think those are the other questions of that
They're
9.
similar. Yeah, they're similar.
Yeah.
We can skip them. You can try.
Oh, could we do?
Yeah, sure, sure, sure.
Could we do 10 only because it's involving 3 that I was talking about?
Okay, okay, 3. Yeah, yeah, sure, sure.
Yeah. Then we can move on.
Yeah, yeah. Please read.
So 3 events A, B, and C are such that probability of A is 0.4, probability of B is 0.7, and probability of C is 0.4. And probability of A and B is 0.3. So given that A and C are mutually exclusive, and that B and C are independent. So that means you can't draw the Venn diagram like that.
As soon as I see the question of 3, I actually put them together. Right?
When I read it, you were like intersecting them.
Good.
So it would be like a line, wouldn't it?
Given that A and C are mutually exclusive and that B and C are independent, so now the Venn diagram will be A and C are mutually exclusive. So there is no
like the
connection
Olympics.
A and C. Is that clear to you? So
Yeah.
A and C are mutually exclusive. Now we have the other thing, which is B. So let me write down A and C here. Then we'll,
B is in between them.
B is, yeah, B is everything. So let me just say B is like, is that clear to you? So
Yeah.
that is B. Is that clear? Now let's see. So 3 events A, B, and C are probability of A is given to us, B is given to us, C is given to us. Intersection of A and B is given to us. So intersection of A and B is 0.3.
Yeah.
Okay. And this is mutually exclusive, and B and C is independent. So when I say B and C is independent, that means probability of B intersection C, let me write down.
Probability of B intersection C equals probability of B times probability of C.
Perfect. Which
so that's 0. Yeah.
0.7 times 0.4.
0.4. 0.28.
So that is 0.2. Is that clear to you?
Yeah.
Now, once we know these intersections, the things are much simpler. So probability of A is 0.4. So from 0.4, if I take away 0.3, I get only 0.1 left. Then B is 0.7. So from 0.7, take away 0.3 and also take away this 0.28. What do you get?
Oh, 0.12. Wait, so just a quick question.
Yes,
because it talks about A and C, the relationship, and B and C, the relationship, but it is not talking about A and B, like a relationship. So can we assume that those two those two are attached and you can't just write B and C and then A somewhere else?
No, they have given you that A and C is mutually exclusive. So nothing common between A and C. And now they've also given you intersection of A and B. So we clearly have 0.3 there as an intersection.
Oh, right. Yeah, they gave me the question. I didn't see that for some reason.
Now,
okay.
Now the probability of C is 0.4. So 0.4 we have to take away 0.28.
28, yeah. We get 0.12.
So that becomes our Venn diagram, okay? And now we can answer, what is the probability of B intersection C? Well, we just figured it out, 0.28, right?
Yeah, I'm just trying to find the outside.
Okay, now, yeah, outside
is 0.08.
So now let's plug this, right? And 0.08. Very good. Now that is very important to find, especially when you have complement of any event, right? So you have to
includes the outside.
The outside, yes.
Right.
You're right. The probability of B when C has already occurred. So we have to now look into the domain of C, and probability B is 0.28. So we can write 0.28. That is the intersection of B and C. And the probability of C,
Okay.
which is given to us, is 0.4. Do you see that how easy it is?
Yeah. So 0.7.
Yeah, 0.7. Next one, probability of A, not B. So the denominator will be 1 minus B, correct?
Yeah.
And probability of A is what? So intersection of not B is 0.1, correct?
Yeah. So that would be oh wait. So that would be A and not B. So not B would be everything outside.
So 1 minus
Um,
0.7.
including A. 0.1. Yeah.
0.1 divided by 1 minus 0.7, correct? Not
So divided by 0.3. A third.
okay.
A third? But like 0.3 recurring.
Yeah. Okay. Now next one is probability of A, B intersection C, not A. So not A means 1 minus A is 0.4, right? So in this case, denominator will be 1 minus 0.4, which is 0.6 now.
But how do you use the formula? Because there's B and C in there.
No, but when not A. So the denominator is not A, the probability of not A.
Yeah.
So that comes in the denominator.
But the numerator is going to be weird.
Yeah, numerator will work out, don't worry.
Oh, okay.
The first thing, denominator, right?
Yeah.
So numerator is the intersection of B and C, which is common with not A, correct?
Okay.
So let's look at it. So intersection of B and C, which is only this portion for us, and which is common with not A. So outside A, this is there, and therefore it is 0.28. You get the idea.
Oh, yeah.
So if you understand the concept, then from the Venn diagram, it is very easy to write down the answer. However, if you're looking for some equation or a formula, you can't easily do these questions.
Oh, okay. Wait, so the last question, so do you just mind re-explaining that last part with the numerator? Yeah.
So we have in the numerator probability of, let me write down B intersection C, and with this, we are doing intersection of not A. You get the idea?
Oh, okay.
So
the given can be written as
or
like
not A, not A is all this, right? Not A is all this. Is that clear to you? And within that, outside of A, the only region where B intersects C is this region.
0.28.
0.28. So he wrote 0.2.
I see. That's clear. Oh, okay.
Which helps.
Yeah, definitely. You can't do that without the sketch. That's gonna be so hard because you can see it clearly from the sketch. Whereas if you used a formula, you'd be here for days. And it's only 1 mark, so you don't want to be there for too long. Yeah.
And see, you must have realized one thing. I always do 1 minus B, right? So that means whether I calculated this value or not, it doesn't really matter to me because I don't use that value. You get the idea?
Oh, yeah.
I always do 1 minus B, 1 minus A. So that takes care of everything else. And that is better. Rather than adding so many little things together, you might miss one even in the calculator punching.
Yeah.
You may get a wrong. So 1 minus the event is actually very, very good. That's the complement of an event, correct? So it's the definition. So follow that. Is it okay? Yes, of course.
Yeah.
When you want to make a Venn diagram, it has to be complete. You have to say what is outside, correct?
Yeah. You're just saying when calculating, you might as well do it with the values given 1 minus because it's safer and less room for error. Yeah.
If this value 0.08 is wrongly calculated, all your answers will be wrong.
Yeah, we're very risky. That's true. Okay. Yeah.
So make your solutions independent of your calculations.
Oh, okay. That's a good play on words, sir. Very relevant for this topic. That's nice. Okay. I think I can do the rest of these questions. Sure. I think you've taught me the fundamentals, so I think I can.
Great. So we'll conclude on this basic probabilities, how we did conditional probabilities with the complements and with 2 events, with 3 events, right?
Yeah.
and the Venn diagrams, right? So can you summarize, Emmy, now what did you learn in our first part of finding probability, conditional probabilities using the Venn diagrams?
Yeah, so we kind of touched upon the main like two formulas, which was the independent event formula, which was the probability of A and B, like the intersection part equals the probability of A times the probability of B. Then we also quickly touched upon the probability of A union B, which can easily be derived from sketching it, because it's really understandable that the intersection is like shaded in or like counted twice, so that's why you would be subtracting it. And then exclusion and inclusion, so that's the name for that technique. And then you've got your conditional probability formula, which was like the probability of B given A. We want to find the intersection of that over whatever's occurred, the probability of that.
But like domain. So the restricted, you should say the, I always say domain, but restricted outcome.
Oh, okay.
Restricted outcome, yes.
Yeah. And then like the last question we saw, which involved like B and C given not A. It's like you've got the formula there, but obviously the formula didn't work in that case because we had to sketch it. And then yes, we could use like ways of the formula, but at that point we needed to like look at the diagram and just see it literally shading in things and figure it out. So you can't always use the formula, but it's good to have that at hand.
Perfect. So,
have both.
Correct. So that beautifully summarized. I think it should be very good to understand even for our viewers. Okay, so that's the first part. Now the second part, let's continue.
Okay.
We can continue with I saw the tree diagrams there on the right-hand side. So now can you share that? We'll look into probabilities using tree diagrams.
Yeah.
Okay. 2.5, tree diagrams. Can you please read what is mentioned here?
So conditional probabilities can be represented on a tree diagram. So they've like displayed one here. The probabilities on the second set of branches represent the conditional probabilities of B, given that A has or has not happened.
Correct. Okay.
So they've given example 8.
Let's go back once again. Let's see a formula which was on intersection formula. So as you can look here once again, the probability of A intersection B is probability of A times this. Do you see? So when we are moving along this path, you see that? Then you have to multiply each probability along the path. So when you make a tree diagram,
right,
the end result of the probability is the product of all events which have occurred in the sequence. So probability of A intersection B is probability of A times probability of B when A has occurred. You get the idea, right? So direct formula, we have got this. This is what we had been saying, right? If I
we multiplied the other one.
If I rearrange this formula, I get probability of B when A has occurred is basically probability of A intersection B over probability of A. So with the tree diagram, you can easily explain your conditional probability formula. You get the idea?
Oh, yeah.
That's your formula,
right? That's nice. I like that.
Yes.
It's so nice to back up something so easily. Like, you know, when people ask, like, oh, so how did that formula come about, kind of thing. It's so easy to like improve it with the tree diagram. I like that.
Correct. So now let's move forward.
All right.
Sometimes you miss all this, right? These are the key things which make things much simpler to understand later on.
Yeah, and it's because we don't stop to understand this, then you start struggling when it gets really complex because the basics are not there in your head. Yeah, okay. I agree completely.
Let's get into example 8.
Yeah, so a bag contains 6 green beads and 4 yellow beads. A bead is taken from the bag at random, the color is recorded and it is not replaced. A second bead is then taken from the bag and its color is recorded. Given that both balls are of the same color, find the probability that they are both yellow.
Okay. So a very important thing is we are not replacing. Since we are not doing it is without replacement, that means it is a conditional probability. This is a dependent event. It is not an independent event. the
Yeah.
probability has changed. As soon as you take away something from the sample space and do not replace it, in that case, the sample space has been changed, and therefore the second event has a different probability, is dependent on what really occurred earlier, correct? So we are definitely getting into the conditional probability case. Is that clear to you?
Yeah. Yeah.
So now let's read this question once again. A bag contains 6 green beads and 4 yellow. So that is to begin with. There are 10, right? Total. A bead is taken from the bag at random. The color is recorded. So it could be either green or yellow, correct?
Right.
So that is
Yeah.
how we get these two branches. A second bead is then taken from the bag and its color is recorded. Given that both its balls are or beads are same color, both are same color, find the probability that they are both yellow. So we have restricted the domain to both same color, right? So green, green,
Yeah.
yellow, yellow. You get the idea? So we have restricted the domain to these two. Do you see that? Both same color, correct?
Yeah.
So given that both are same color, find the probability that they both are yellow. So they both are yellow. So this product will come in the numerator, correct?
Right.
They
Yeah.
both are yellow, correct? So that comes
Uh,
in the numerator, right? And in the denominator, there are two parts. Either you could go for two greens or you could go for two yellow. So
yeah.
they
Yeah.
add up. You see they add up in the denominator. So that becomes your restricted sample outcome. You restricted outcome, correct? So add
Yeah.
these two probabilities. So that becomes your uh, denominator in this particular case, and you can solve to find the solution. Is that clear to you?
Very clear. So timesing those two probabilities because there's two ways of achieving the same color balls.
Now, in such questions, very important thing is how do we define an event? So that is actually kind of missing here. How do we see the formula is given here, right? I do agree with the formula. Probability of B when A has occurred, right? And the formula is there. So tell me,
Yeah.
what is the event A and what is the event B?
What is the event A?
Yeah,
Um, it's where you get the same color.
both same.
Yeah. So both greens or both yellow.
And event B is
Event B is where you don't get the same.
both green. So B is both yellow, correct? So that is what you have to find. Given that both balls are same color, find the probability that both are yellow. Is that okay? So very important
Yeah.
thing is when you are attempting the same question in examination, you have to define your events. You cannot go directly with the solution. That's what I will recommend.
Oh, okay.
You
Yeah.
might lose 0.5 marks for not writing this statement.
Right. So defining the
Event A and event B. You cannot
defining.
randomly write A oblique B and use the formula. No, you cannot.
Oh, right. Okay.
So define your events. Is it okay? So make a note of that.
Yeah.
So look into my YouTube channel, many examples on this, especially when we work with biased coins. This is very interesting, you know. Normally flipping a coin is 50-50.
It's fair.
But when
Yeah.
it is a biased coin, then, you know, these tree diagrams make things very simple.
All right.
Yeah. Okay, let's continue. Take
So
any,
yeah. Sorry.
take any question.
Oh, okay. Yeah. Let's do the ones with the
Yeah,
red
see,
on it.
see. Okay, let's do that. Yeah.
Okay.
Please read the question.
So a bag contains 4 blue balls and 7 green balls. A ball is selected at random from the bag and its color is recorded. The ball is not replaced. A second ball is selected at random and its color is recorded. Part A, draw a tree diagram to represent this information. Yeah, so that's nice and easy.
That's easy. That you can do, right? So
yeah,
very simple. We just have
blue and green.
Yeah, blue and green, right? So there are 10 in all. It is actually similar to exactly. So if it is 4/10, right? We are talking about the blue stream here. And it is 7 Oh, 4 and 7 is
Wait, so
11.
how come it's? Oh yeah,
11.
just about to say.
Yeah, 7 over 11, correct. When it is green, correct. Now,
Does it matter that you just write BG, BG, or do you have to write B1 and then B2 on the next branch?
no, B is okay because from the tree you can see the steps, right? A
Oh,
sequence is
that's true.
being followed. So when you pick a ball, it could be either blue or green. There is no other
Yeah.
option, correct? So you
Right,
got
right.
blue G, right? Now when you pick a ball, again there are two options, correct? For
Yeah.
both the cases. So it could be again blue or G, correct? So in the first case, since you picked up a blue, now you got only 3 blues, right?
Yeah.
So this is 3 over 10 because one ball is reduced, correct?
Oh yeah. So that would be 7 over 10 because that hasn't changed.
Yeah, and this is 7 over 10, you're right. And in this case, you picked up a green, and therefore one green is less. So 6 over 10 is when you get, okay, but it's better to write green at the end. So let me write, sorry. Uh, okay, let me clear this. It's better to, follow a path. Like, let's put this as green, green, and let's put blue here, right?
Yeah.
So in case we picked up green first, all 4 are there, so 4 over 10. And then in green, we have 1 less, 6 over 10, correct?
Yeah.
So that gives you the combinations required. Now the question is, that's the tree diagram. So you can actually, over here, write on the products, 411 times 710, 310, right? So 4 times 3, yeah, let's write down like this, 411, 310. Is that okay?
Okay.
And here we'll write 411 and 710. And then we have 711 and 410. And here we have 711 and 610. Is it clear to you?
Yeah.
We have each individual thing mentioned on the tree diagram. Find the probability that the second ball selected is green. So we are only interested in finding the probability of second ball being green, right? So second ball could be green in this case and in this case, correct?
Yeah. So you add them.
Yes.
Cool. So we got 4 over 11 times, is it 3 over 10?
Yes.
Yeah. 3 over 10. And sorry, I'm not really a fast typer on the
No
calculator.
problem. No, you take your time. Yeah. You can
20. Oh, sorry, 27 over 55.
okay, I'm just going with your values.
Oh, right. Yeah.
Both balls selected are green, given that the second ball selected is green. So you are using first solution in the denominator, right? So you have 27 over 55 in the denominator. And both balls being green is this, 7 over 11.
7 over 11 times 6 over 10.
Correct. So that is how you're going to solve this. Clear?
Very clear.
Perfect. So we'll erase this and move on to something else.
It's 7 over 9. It's a nice number.
We'll calculate. That's fine.
Okay. Question 10.
Okay, sure. A box A contains 7 counters, of which 4 are green and 3 are blue. Box B contains 5 counters, of which 2 are green and 3 are blue. So we have A and B, 2 boxes. You see that? Now, this is a very tricky question, actually. Box A contains 7 counters, which are 4 green, 3 blue. Okay, let me write down 4 green.
4 green.
Box B contains 5 counters, 2 green, 3 blue.
2 green, 3 blue.
Correct.
Yeah.
A counter is drawn at random from box A and placed in box B.
Oh.
The second counter is drawn at random from box A and placed in box B. So again, it has been placed box B, right?
What happened if it was the same counter?
Pardon?
What happened if it was the counter that you took from A into B is the one that you took from B into A?
No, they are doing from one box only, right? A count, because there are 7 here and 5 there. So a counter is drawn at random from box A and placed in B. So You actually just pick one and put it here.
Yeah, but I mean from like the second time you do it, imagine if you take the counter that you just took from A and that's the one you pick up and you put back into A.
No.
This is random.
Second counter is drawn at random from box A again. Second is
Oh.
also from A to B.
Oh,
Second is
so
also
it's
from
drawn
A
from
to
B.
B.
Yeah,
Right.
yeah.
A third counter is then drawn at random from the counters in the box B. Then the third one is from B.
Oh.
For this, you have to draw a tree diagram to show the situation. You get the idea.
Oh my God, there's a lot going on. Okay.
Lot of work. So I think we'll leave this for now. You should actually draw this. This is a much bigger diagram. So basically, what we have to do is that, well, the tree diagram is something like this. We are looking into counter A. Yeah, we need more space. Yeah. That's better. Right? So we'll look into this. So we are first looking at A, correct? So in A, there are 4 plus 3, 7. And we could draw either green or we could draw blue, correct?
Yeah, so 4 out of 7, 3 out of 7.
Yeah, so three are blue and 4 are green. So 4 out of 7 and 3 out of 7. Correct. This is your first draw. The second pick is again from A. So we'll again go ahead and we'll pick here. Now, it could be again green or blue, right?
Yeah. But because it's not replaced, does it mean it goes down?
No, only the numbers will change to 6, right? Instead of 7 now?
Yeah, but like 3 over 6.
Yeah, but 3 over 6. Yeah, just as we did earlier. So it's complicated, but it is not. Once you make the tree diagram, it is going to be bigger, but not difficult. You get the idea, right? So blue was not drawn. So we already have only 3 blues, right? So 3 out of 6.
Yeah.
Okay. And so that is the situation after 2. And on this side, 3 out of 7. And we draw blue, not green. So green are still same, which is 4. 4 out of 6.
Then 2 out of 6.
2 out of 6. Good job. So we have done the 2, right?
Yeah.
Now, if that is the case, that everything is going actually into C, right? So the quantity in C changes. You get the idea. Because
the total.
I mean, what I'm trying to say is the second box, envelope, whatever it is, right?
Yeah.
Now you're drawing one from C, right? So let me just make a big box here. This is the second envelope because everything went into this, correct?
Yeah.
So box A, and this is box B. So let me just say box number 2, or I may say B, whatever, right? And now you're drawing. Now what do you need to do? When you draw from here, what could you get? Now, depending on how the tree came, so if you come from first, we can actually go ahead from here, correct? And you could now draw either blue or green, correct?
Yeah.
Now, at this stage, in this place, we already have 3 green, 2 green, and 3 blue. Is that clear to you? We have 5.
Oh, yeah.
We have 5 there already. Is that okay? 5 already, correct? So we have already 5 there, and 2 have been introduced in them. So there are now 7.
Yeah.
Out of 7, you are going to draw something, correct? Depending on what path was taken to reach here earlier. Is that clear?
Oh, yeah. Yeah.
Now, if you take the first path, that means you got both greens, correct?
So yeah, you got both greens.
So now you have to draw 2 here. You got both greens. That means the greens, which were earlier 2, now became 4, correct?
So 2 greens were drawn, and because there's 2 in box B, 4 greens total.
4 greens. Yeah. And total number increased by 2, so it is 7.
7. Oh.
You see how we have drawn this green?
Yeah. Oh, I wouldn't have done that. That was tricky. Yeah.
Now, if the blue has been drawn coming from the first path, then Well, no change in blue. Blue was only 3. It remained 3. So it is 3 out of 7. You get the idea.
Wait, why wasn't blue drawn?
Because we are going through first part. All green were picked. 2 green were picked.
Yeah.
So there were already 3 blues. So they 3 remain, but the quantity increased from 5 to 7. So the probability of picking a blue at this stage, so that is green and this is blue for us. Is that clear?
Did you just say that green was picked and not blue? It's like
Yeah. Both green were picked. So now we can look into the second branch where 1 green and 1 blue is picked, right?
Yeah.
So denominator is 7 in each case here when you draw, because we have 2 additional things.
Yeah.
If 1 green and 1 blue has increased, in that case, the probability of getting green is what? Green was 2 and 1 more, so it is 3. 3 out of 7. Blue was 3, it became 4, 4 out of 7. You get the idea.
Oh, yeah.
Similarly, just follow the same pattern and go
For
with
the rest of them.
You get the
right.
idea.
Yeah.
So your tree diagram is now complete. Is that okay?
Oh, that's clear. Yeah. So you have to work them like independently, kind of.
So make a neat and clean chart, because you need to now multiply all these numbers to get the final probability.
Yeah.
Right? So we're going
the bigger the better, because then you're going to avoid any mistakes.
Correct, but this space is too less. So I need a clear, so work it on a clear paper where you could put all of them. But I hope you have understood the concept, right?
Yes,
so
I have.
Everywhere the denominator is going to be 7 only, right? 7 only. But the numerator depends on which path was followed and how many blue or greens were added. Simple as that.
Right.
So if I follow this path, which is like 1 blue and 1 green, 1 blue and 1 green, so we know both numbers will increase by 1, so 3, right? So for getting green, it will be 3. You get the idea.
Yeah.
Getting blue, it will be 4 out of 7. Is that simple as that? If you follow the last part, which is both blues, then green was not added. So green will remain 2, and 2 blues will make it 5, right? So 5 out of, there were 3 blues. So 3 and 2, 5. 5 out of 7. So that completes our tree diagram. Do you see that?
Not when we compare, so when 2 blues were picked, the last blue that we picked, it had 2 out of 6. So if 2 blues were picked, then
so 1 blue, 1 blue. You add 2 blues. So there were 3 already. 3 plus 2 is 5.
Oh, 3 in the box B. So yeah, sorry, I was looking at the 3 where it says there, so confused.
So that tree diagram is now absolutely ready for you. Now from here, you can answer the other question, which should not be difficult at all. Correct?
Wait, so is that it with the tree diagram? You're not going to talk about it going back into A?
No, this is the question, right?
No, yeah.
Zoom in. Can you please zoom in and read the question once again?
You know, it talked about a third counter.
Yeah, we did, right?
A third counter is then drawn.
Third counter.
Oh, yeah, that was the third counter. Yeah.
After that, we are drawing the tree diagram, correct? I mean,
right.
We followed the sequence. Third counter was this changing that quantity from 5 to 7. Is it okay?
Right. Yeah.
Now, can you read the other parts?
So the event C occurs when 2 counters drawn from box A are of the same color, and the event D occurs when the counter drawn from box B is blue. So find the probability of C. Yeah, so that's just using the formula and solving. So, but you would multiply them across.
Correct.
Yeah.
So the event C occurs when 2 counters drawn from box A are same color. So either both, so the top line or the bottom line, correct? So one of those two. So that is the event. And D occurs when the counter drawn from box B is blue. So let's go for blue from box B. Is that okay? So there are a couple of stages where it could be blue, but we'll go with the conditions, whatever conditions they give further, and write down our answer. Is it okay?
Very clear. Thank you, sir.
That's it. So
I think that's probably done.
Yeah. So we'll clear the screen. Can you summarize how tree diagrams can be used to solve questions related to conditional probability?
Yeah, so like we talked about in the beginning, literally deriving the formula that we use for conditional probability, it can be proven using the tree diagrams. Because like I kind of asked a question in between saying like, should we put like B1 and B2? But because the way tree diagrams work, there's already a sequence and a flow to it. So we can see where we started and given that this has happened, what's going to happen. So like that, it's very straightforward when you have just one set here and then two more coming off it. It's when you go bigger and bigger, it kind of gets a little bit tricky, like we saw with the last question. So moving from here to here. So you just have to be aware of that denominators can change and be aware of the initial, how many beads or stuff are in the thing. And then when beads are added or removed, and if it's replaced or not, you need to make sure you counter for that by changing, like adding one, subtracting two, stuff like that. So yeah, it's very important, but like, yeah, just using the formula and like sticking with the diagram. Make sure it's like really big because you can get it messed up and yeah, you don't want to
neat
make
and clean diagram is required. Yeah, that is perfect. So that's the end of your unit on conditional probabilities. So you have learned how to use Venn diagrams to answer the questions and how to use two-way tables to answer your questions, how to use the sample space to answer your questions, and how to use tree diagrams to answer your questions, correct?
Right, or like linking in conditional probability and the independent events and the Venn diagrams. So all in all, it was super helpful, sir. Thank you so much for teaching me along the way, all of it. Yeah, so I'm going to just go
questions from your book. In case there is any difficulty, write to me. We can sort them out.
Okay, thank you so much, sir. I appreciate it.
All the best.
And enjoy the rest of your day, sir.
You too. Thank you. Bye.
Thanks. Bye.